Okay, well, I think we can start now. Good afternoon, everybody, and welcome to the first colloquium in a new semester, in the summer semester. I'm Richard Tufts, and I will be taking us through the semester on the colloquium. I'm taking over from Diederik Kroesjen, and I'd like to start, first of all, by thanking Diederik for his sterling work organizing the colloquium over the last few semesters. This semester we've got a very wide range of topics. We're going to be ranging from very long wavelengths radio to the highest energy photons ever observed by mankind, which come from distant space. And I think one of the things which are going to connect those things together, which will be a recurring theme, will be the sort of connection of astronomy to fundamental physics. And there's nobody better to really do this than Victor Flambaum, who is an expert on so many things. And I will just pass over now to Victor's host, Jose Crespo, who will introduce our distinguished speaker today. And I'll pass over to Jose.
Thank you very much, Richard. Welcome, everyone. I'm very happy to have today opening this colloquial series, Victor Flambaum. Victor Flambaum is full professor, head of the Department of Theoretical Physics of the University of New South Wales in Australia since '91, and Scientia professor in the same university. And he covers in his research an incredibly wide range of fields from the theory side, including atomic molecular nuclear physics, solid state physics, general relativity, astrophysics, the violation of fundamental symmetries, parity, time, Lorentz invariance, and the test of theories of grand unification. He also has developed atomic physics methods for investigations of dark matter and dark energy in atomic and astrophysical phenomena. And he has been author of a very well cited paper on observations of a possible time variation or spatial variation of fundamental constants based on observations made with telescopes. So Victor Flambaum was educated at the Novosibirsk University, where he did his Bachelor of Science and his PhD, whereby he was awarded the Lenin Komsomol Prize, who was the highest prize awarded by the Soviet Union to a young scientist below the age of 33. Then he became Doctor of Science, the full professor, even so there, and then he moved basically to the United States and then to Australia. The United States, he was at the Joint Institute for Laboratory Astrophysics at GELA, at Harvard University as a visiting fellow, as also at Princeton, and he became a member of the Institute of Advanced Studies in Princeton. He was also in Argonne, and again at GELA, and currently he is not only professor in Sydney, but also a Gutenberg Fellow in Mainz, in this network dedicated to the studies of fundamental phenomena. So one can see that a very broad range of experimentalists and other theoreticians have collaborated with him in the variety of fields he has been working on, and there is a younger generation of well-known in the field in atomic physics, young theoreticians who have learned his skills in the school of Victor Flambaum. So today he will give us his insights in the space-time variation of fundamental constants and the effects also of dark matter and dark energy in a possible time variation of these constants. And with this, it's my pleasure to pass the word now Victor. I'm eager to listen to his talk today. Thank you very much.
Thank you for invitation and introduction. So it looks like there are two topics, but it's actually one, because space-time variation of fundamental constant may be caused by dark matter. Now, first I start why it's interesting. By fundamental constant, I mean such constants like fine structure constant, which is combination of electron charge, Planck constant, and speed of light, similar strong interaction constants and particle masses. Why it is interesting? Now, first of all, it's well known that for life to appear, there should be some fine tuning of fundamental constants. So if fundamental constants are even slightly different, life could not appear. And one of the answers to this puzzle was that fundamental constants vary in space. We just happen to appear in the area of the universe where fundamental constants are good for us. It does not mean that we must see variation of fundamental constant in space, because the universe is very big and even maybe infinite. So variation on a scale of visible universe still can be very small. But at least it's worth trying and try to find this variation of fundamental constants. And a more recent interest appeared from theory. As I will show later, interaction of normal matter with dark matter may be a source of variation of fundamental constants. That may be dark matter, dark energy. There is no sharp border. It just depends on the mass of the particles which create the field. Okay, so I'll speak about dimensionless constants, because dimensionless constants do not depend on human units. So if the constant has dimension, you cannot distinguish variation of fundamental constant from variation of units. So it's better to consider dimensionless constants to avoid this question about units. The most famous dimensionless constant is fine structure constant, which is responsible for relativistic effects. It's combination of electron charge in Planck constant and speed of light. There are other fundamental constants like electron to proton mass ratio, for example. It's also dimensionless, but it's not a very fundamental parameter, because proton mass is mostly proportional to lambda QCD. It's strong interaction parameter which appears in strong interaction constant. Running of strong interaction constant depends on lambda QCD. It has the same dimension as mass, so ratio of masses of electron and quark to lambda QCD is another dimensionless parameter, equally important to fine structure constant. These are parameters of electromagnetic interaction. These are parameters which appears in strong interaction. So how we can see variation of fundamental constant? There are many ways to do this. The earliest time we can reach is Big Bang nucleosynthesis, when we have some reliable data. Then we can go to quasar absorption spectra and compare quasar spectra, which is far, far away and long time ago, with current spectra. Then there is Oakland nuclear reactor. Very popular area is atomic clocks, which have very high precision of measurements now. And we can look for enhanced effects, where instead of high precision, we have effects which are very big and compare the effects of atomic clocks and may be easier to measure. These enhanced effect may exist in atoms, molecules, and nuclei. And also the popular topic is dependence on gravity. Can fundamental constant depends on gravitational field? So far, there is some evidence in quasar absorption spectra, but it has not been confirmed by other measurements, so it's still waiting to be confirmed or rejected. So I will start from these spectroscopic properties, where we can measure spectra. It will be spectra in quasar spectra or spectra in laboratory, and try to detect if there are any variation of fundamental constants there. So to go this way, we performed calculations of atomic transition frequencies, how they depend on fine structure constant. So for example, if it's optical transition, where it mostly depends on fine structure constant and appears during relativistic correction, because fine structure of an atomic spectra is due to relativistic corrections. So we know transition frequency in laboratory for current value of alpha, omega 0. And if alpha varies, there is additional term here with some proportionality coefficient Q. Q must be calculated. We cannot determine it from experiment. This is why we need to know how atomic transition frequencies depend on fine structure constant. So we calculate this coefficient Q. We calculated it for all available lines in quasar spectra, in quasar absorption spectra, also for all atomic clocks, for current clocks and future clocks, for highly charged ions, which are studied in Heidelberg and MPQ. We also calculated it for nuclear clocks, microwave, hyperfine clocks, and here, when we go to nuclear clocks or hyperfine transitions, there is also sensitivity to strong interaction parameters, which I mentioned, this lambda QCD or ratio of electron to proton mass. So it's a big activity which lasted for many years, but we prepared and now we can go to what was observed. So this is results of calculation of spectral lines which are observed in quasar spectra. So this is astrophysical application. So as I told, we calculated this coefficient Q, sensitivity to alpha variation, yes? And there are three types of line. There are anchor lines. It's mostly light atoms because relativistic effects are proportional to nuclear charge squared. If nuclear charge is small, this transition have little sensitivity to alpha. When there are negative shifters, it means that transition frequency decreases if alpha increases. And there are positive shifters. It's a case when transition frequency increases when alpha increases. We know why we have such a variety. As I told, for light atoms, there is no sensitivity because relativistic corrections are small. But negative and positive shifters may appear in more heavy atoms. And the difference appeared because there are different transitions. All these atoms have S and D electrons in open shells. And if you remember hydrogen spectra, you know that relativistic corrections give positive contributions to sp transitions, the transitions of s electron to p electron. So it's L equal to 0 to L equal to 1. So they have positive contributions of relativistic correction. It means that frequency increases when alpha increases. But if you excite d electron to p states, relativistic corrections are negative in this case. So it's higher wave to lower wave. Relativistic corrections are negative. And we have a negative shifter. So frequency decreases when alpha increases. It's important to have all possible cases because this allows us to measure effect. We need different dependence of different transition frequencies on alpha, and it allows us to control systematics. So even the same atom may have different shifters, as I told. For example, nickel may have anchor line and negative shifters, or iron, it has negative shifter when d electron is excited to p state, and positive shifters when s electron is excited to p state. So there are also many other transitions which I have not listed here, but they're still observed in quasar absorption spectra. So all this variety is used to measure alpha variation, variation of fine structure constant. What is important here? Different sign of effects for different transitions. And systematic effects do not know about the sign of the effect, what is the sign of Q. They are not correlated. So it's important to have this variety to measure effect and find systematics. What we have now, so this is quasar absorption cloud, And we see some absorption spectra there. But when we compare them with laboratory spectra, if we calculate ratio frequency, redshift cancels out. So it's a clean case. Redshift cancels out if we compare ratio frequencies, or just use redshift as one of the fitting parameters. So all we need to do is to find out how much of variation of alpha is needed to see this difference in transition frequencies. So for this, we need calculations, which we performed. So we did calculations, and my colleagues and co-authors made measurements. And what we've got? We've got an amazing result. Again, it still has to be confirmed, but fine structure constant varies in space. So you look in one direction, you see one value of fine structure constant. Another direction, you see another value of fine structure constant. This is a plot which covers the nearly whole size of the universe, more than 10 billion light years. It's everywhere where quasars are available. So significance statistically is pretty big. It's more than 4 standard deviation. But still, we need to know something about systematics. So there are some arguments that it's not fiction, because there are 2 telescopes which use completely different spectra, analysis of data, and so on. And the results from both telescopes are consistent. This is a direction of a gradient here shown on a sea of skies. Consistent, the same direction and similar magnitude. Then we have another test. It's high redshift and low redshift. Because for high redshift and low redshift, we use different species, different transitions. So again, test of independence, and they give reasonably comparable results. So they agree with each other, high redshift and low redshift. So we have some consistency tests. So different telescopes give the same results. So independent samples, different data, reduction procedure, different instruments and telescopes. And high and low redshift effect also agree. These gradients of dipoles, astronomers call them, agree. Different species used at low and high redshift, and different transitions respond differently to the same change in alpha. As I told, there are negative, positive, and shifters and anchor lines. So where initially it was kind of 300 absorption systems and 30 lines. It's the biggest sample ever analyzed for this purpose, because other groups never considered more than 20-something transitions. Again, it's not a final proof yet, because its results were obtained by one group. But John Webb, who is very enthusiastic, also checked are there any similar kind of gradients in other data. And it seems that there is some gradient in Planck satellite data, so some asymmetry in the universe. There is there's asymmetry in CMB fluctuations in different directions. There is some hint for possible asymmetry in dark energy supernova data, metaflow, agree with alpha dipole, and so on. So there are some hints, but it's still not a proof. At least according to John Webb, who was very interested to see it, and he was a leader of measurements, they all show in the same directions, all these effects, but we still need more. So, of course, we tried other examples. For example, one of my favorites is ammonia molecule, NH3. The reason is that effect is enhanced there, because there are 2 closed levels in ammonia, and the splitting between these levels appeared due to tunneling of hydrogen relative to nitrogen. So tunneling, if you remember quantum mechanics, has exponentially small probability. So splitting of these inversion levels in ammonia is exponentially small, so it exponentially depends on the parameters of the system. In this case, it's ratio of electron to proton mass. So it's good. We have enhanced sensitivity to variation of electron to proton mass. So far, there are some measurements, but there are only 2 systems, and people only can get limits. So I participated in the first work and a little bit in the second work, but the results are only limits because there are only 2 systems. You hardly can tell reliably about any gradient of variation of electron to proton mass having only 2 data points. Then there is another example, which is most popular molecule in the universe, is hydrogen molecules. But again, there is some hint for gradient, but statistical significance is very low. So we did our best to find other examples in spectroscopy. There is no contradiction, but there is no reliable confirmation also. Then Big Bang nucleosynthesis. It's one of our favorite fields to search for variation of fundamental constants. It depends on fine structure constant, but more strongly it depends on strong interaction, because Big Bang nucleosynthesis is a strong interaction process. It's a plenty of work on this topic. The only, I can say, useful conclusion, there is famous Lithium-7 problem, when predictions of Lithium-7 give bigger abundance than it was measured. And by variation of this strong interaction parameter, quark mass over lambda QCD, you can eliminate this problem. So it's good. You can say, okay, another evidence for variation of fundamental constant, but it's probable that there are other reasons. It may be not the only reason and not the only solution for lithium problem. So it's a good hint, but again, it's not a proof of variation of fundamental constants. So we can try spatial dependence. But the spatial dependence is only good for deuterium, because deuterium abundance is measured in very distant objects. Other abundances are measured nearby. So we have 7 points for deuterium, and we try to find gradient in the distribution of deuterium abundance. Again, there is some hint, but here it's very weak. It's something like 1 standard deviation in the gradient. So this is a work for future application, and there will be more measurements of deuterium abundance on big distance and higher accuracy. Maybe in this case, you can find a reliable statement about if there are any gradient in deuterium abundance exist along the universe, and if this is indication of variation of fundamental constant. So you see, all these examples are attempts to find if universe is symmetric or not, and how it reflects in the values of fundamental constant in different parts of the universe. Okay, so what to do? Are there any other tests possible? So, okay, we finish with astrophysics for a moment and see, can we check this gradient in laboratory? Again, it's gradient in space. In laboratory, we do time-dependent measurements, the dependence on time. But we are moving. Galaxy is moving, sun is moving, Earth is moving, it rotates around sun. And we can see, okay, if we believe that astrophysics give us a good value of gradient of alpha, we can calculate how fast will be variation of fundamental constant in laboratory, because we are moving. So, and this estimate give us, and due to sun motion, we have something like 10 to the minus 19 is 10 to the minus 11, but there is also cosine of an angle. We are not moving in quite right direction. So its effect is about 10 to minus 19 per year. Earth motion, it's even producing even weaker effect, because Earth is slow. Sun moves 369 kilometers per second, and Earth moves only 30 kilometers per second. So effect is 10 to minus 20, but we have annual variation. You can may look for annual variation of fundamental constants. So this is a picture just showing all this motion. Galaxy moves, sun moves, and Earth moves. And gradient of alpha in this picture looks down. So you can see that angles are not very favorable, but still we're moving towards area of bigger alpha. if we believe in quasar data. And this reflects in time-dependent variation of alpha. Alpha should increase in this case with time. So as I just repeat, we did calculations for all available atomic clocks and other possibilities where one can see variation of fundamental constants. So it's dependence of transition frequencies in optical region, in microwave region due to hyperfine structure. So for optical region, we measure variation of alpha. For hyperfine structure in molecules, it's maybe electron to proton mass ratio and strong interaction parameter, quark mass over lambda QCD. So we proposed a variety of methods to detect variation of fundamental constant in laboratory. And there are a lot of measurements with wonderful, fantastic specialists, including Nobel laureates. So I presented only a few works, but there are many of them. And there are recent works which I have not even listed here. For example, there is a wonderful work, maybe most accurate measurements now, which is done in PTB in Braunschweig. So not pretty close to Heidelberg. But conclusion is that it's hard to go to 10 to the minus 19 per year. Again, the people are doing fantastic job. They have measured up to 18 digits in frequencies, but still variation of alpha is about 10 to the minus 17 per year, or even better than this. But it has not reached 10 to the minus 19 per year, which is needed to test astrophysical results, variation of fundamental constant in space. So no groups who are doing these measurements so far claim that they detect variation of fundamental constant. They only obtain limits. And it does not contradict to astrophysics because request of astrophysicists is very tight, 10 to the minus 19. We are trying to help experimentalists. We are looking for situation when variation of frequency is much bigger than variation of alpha. Yes, so sensitivity coefficients should be very good. One of the first example which we propose is dysprosium atom. We're especially looking for this case in all atoms and transitions. In dysprosium atom, there are two very close levels. They have even opposite parity, so have electric dipole transition between them. In tables where have exactly the same frequencies of transition, so with exactly the same energy, so frequency of transition would be 0. But actually it's not 0. People did more accurate measurements, and interval between these levels is different in different isotopes. So it is so small that tiny isotopic shift change relative position of these levels. So absolute shift is not enhanced here. It's just typical value of Q for heavy atoms, something like 20,000. But one of the levels is positive shifters, another negative shifters. So if alpha increases, this interval will change, and it change in different way in different isotopes. So it's good. One frequency increase, another decrease. So it's excellent control of systematic effects. So one frequency increase, another decrease. And effect relatively is very, very big. Enhancement is up to 6 orders of magnitude in one isotope and 10 or 8 orders of magnitude in another isotope. This is relative enhancement. It's because we have 0 in denominator. People measure, it's a Butker group who measured frequency of this transition. And because this frequency is extremely small, delta omega over omega is extremely large, just because you have near 0 in denominator. So it's a relative enhancement. Excellent case, but there is one disadvantage. One of the levels is broad, it decays. So it's basically experimenters reach a limit. They already measured frequencies with accuracy much better than the width of one of the levels and cannot go further because the level is too broad. Advantage of this transition is that you don't need 18-digit accuracy. 10 digits accuracy is enough to compete with atomic clocks. There is another example, molecules. In molecules, there are also close levels. and they are narrow. I mean, they live long time, so we don't have this problem with short lifetime. But there is no experiment yet with molecules. The people only started doing this. Then another example is highly charged ions. This is leading place for this study is Heidelberg, and in particular Jose Crespo and other people in his co-authors from Heidelberg and PTB Braunschweig. Again, this is the beginning of a road, but I try to explain why highly charged ions are so good. The point is that relativistic effects increases in highly charged ions. So sensitivity to alpha variation highly charged ions is much bigger because these ions are small. It means electrons are closer to the nucleus, and electrons move faster than the nucleus where potential is big. Potential is big, it means kinetic energy is big. So there is a big enhancement of relativistic effects, and consequently big enhancement of sensitivity to variation of fine structure constant. But there is one disadvantage. Transition frequency are big and they go off laser range. So we have especially looked for close levels in highly charged ions. We select levels when they're very close to each other and their spectra or the transition between these levels go into laser range. And fortunately, Jose and his co-authors found that these transitions indeed exist in highly charged ions that have small frequencies. So in laser range, relatively small. It's not X-ray, it's optical. And future atomic clocks with highly charged ions have very bright, future is very bright for these systems because there is strong sensitivity to alpha variation enhanced by some 100 times, for example. And also highly charged ions can make a very good clock because systematics is much smaller, like black body radiation shift is proportional to third power of the size of a system, and size of highly charged ions is small. So both smaller systematics potentially and high sensitivity give highly charged ions a good example. And here we have absolute enhancement. So in atoms and molecules, we consider relative enhancement. So delta omega over omega enhancement. In highly charged ions, it's both relative enhancement and absolute enhancement. So shift due to alpha variation itself is bigger. Even better example, in theory at least, are nuclear clock. Nuclear transitions are somewhere in 100 keV, MeV range. So it's, of course, it's very far from lasers. But to have high accuracy, we need to use laser spectroscopy. But there is one wonderful example, is thorium-229. And there is a lot of activity about building nuclear clock with this isotope thorium-229. And what we also found, that this transition, because it has small frequency, it has huge enhancement of effects of variation. Both alpha variations and enhancement about 4 orders of magnitude, and enhancement of strong interaction parameter, like quark mass over lambda QCD. So if this clock will be ever built, it's a perfect example, because it's both a relative enhancement, the frequency is not MeV, but electron volts, and also absolute enhancement, because nuclear effects are much bigger than atomic effects, some nearly 1,000,000 times bigger in principle. So in atoms, we speak about electron volts, and nuclear and MeV. So this is our result of calculations, enhancement about 4 orders of magnitude. And our recent activity is related to Mössbauer transitions. Mössbauer transitions also have very high stability. So shifts can be measured, say, 10 to the minus 18 and so on. Of course, we cannot measure absolute values of Mössbauer transitions very accurately. There is a lot of effects from solids and so on. But we can check if frequency changes. For example, we can have 2 separated sources of Mössbauer transition. One will be source, another absorber. And we can check spatial dependence of fundamental constants, just because of the different locations. So this is basically theoretical part. Experiments have been done only with Dysprosium, but there are big opportunities here with enhanced effects. And final topic of my talk is relation to dark matter. As I will explain in a few minutes, that dark matter may cause variation of fundamental constant. And this means that searching for variation of fundamental constant, we may detect dark matter. It's another method of dark matter detection, a new method which is explored recently, theoretically and experimentally. So some very little introduction. People search for dark matter in scattering experiment. There are many underground laboratories which are looking for dark matter. But when you consider dark matter scattering experiment, the effects are proportional to 4th power of interaction constant, because amplitude has 2 vertices, cross section is amplitude squared. So 4th power 4 of interaction, which is assumed to be extremely small. This is the reason why we don't see the effect. Interaction between dark matter and normal matter is very small. So interaction small, it's very hard to detect this. So this is maybe a reason why people still don't see dark matter in scattering experiments. What I want to discuss here are linear effects in this very small interaction constant. Linear effect means we have enormous advantage because interaction constant is very small. And why do we have linear effects? It's specific to low mass dark matter because people have not found heavy dark matter yet, but there are very popular candidates for low mass dark matter. Some scalar particles, pseudoscalar particles like axion, which have low mass. And what does it mean for us? It means that these low mass particles form a field. Because if mass is small, we need a lot of these particles to saturate dark matter. So we have very many particles on a volume of a size of wavelength. So instead of specific particles, we have field. It is similar to photons, which form electromagnetic field. We have many photons. We can forget about their quantum properties and see only some electromagnetic field produced by these photons. The same situation here. If we have low mass of dark matter particles and we assume that they saturate dark matter, we can treat them as a field. Yes, and this field produces observable effect. And there is another feature here. These particles are cold because the universe expands, they're cold. The kinetic energy is small. If kinetic energy is small, the energy equal to rest mass, so mc squared. So it means all these particles have the same oscillation frequencies. Yeah, so we have field which oscillates coherently. So if this picture is correct, we can say that nature made us a present. But it made us a cosmic maser consisting of scalar field. So it's coherent radiation of scalar particles. And it, of course, if there is interaction, we can try to detect this field. Unfortunately, mass is not known. So we don't know frequency of radiation. This is a major problem. We need to find, scan the big area of possible masses. Okay. So I can show another picture explaining the same effect. So very early at the lifetime of the universe, some scalar field was produced, like other fields, like other particles. So it has non-zero value initially. When the universe expands, initially this field is frozen. It cannot do anything. It's just solution of Einstein equation for scalar field. If mass of a particle smaller than Hubble constant, it behaves like dark energy. So it corresponds to nearly constant field. So it practically does not evolve. So for example, this field may produce accelerated expansion of the universe, but it happens on a short time scale because when mass is smaller than Hubble constant. Of course, as mass is extremely small, and smaller than Hubble constant now, we still may deal with dark energy. But probably mass is not that small, so only initially it is frozen. When universe expands and size becomes sufficiently big, Hubble constant small, where oscillation starts. So this field oscillates around its minimum. Near minimum potential is quadratic, and this quadratic potential has mass as a coefficient, because this is expansion of energy of a field, and mass is a coefficient. So we come to the same picture, but whereas oscillation with a frequency of mass. Of course, I used units h equal to c equal to 1, so it's relativistic units, natural units. So frequency equal to mass, and we have here oscillation of a field, which continues up to now. If mass is small, like smaller than 24 eV for QCD actions, for example, these particles survive to the present day. So if mass is not very big, they are practically stable. Okay, and here we have two roots. Because scalar particle may be real scalar, so it does not change sign on the coordinate reflection, or it may sign on the coordinate reflection, and so pseudoscalar particles. And we should look for different effects here, because if it's scalar particles, positive parity, or it may be pseudoscalar, but with field squared, it's also will have positive. P squared always have positive parity. We speak about time variant fundamental constant. So interaction with scalars, it's interaction with density of normal matter, produce effects of time variant fundamental constant. And on this way, we achieve 10 to 15 times improvement, 15 orders of magnitude improvement in comparison with previous limits, up to 15 orders. It depends what interaction we consider, because effects are linear. If particles are pseudoscalars like axion, we consider time-dependent effect. It's a completely different story. Time variant spin-dependent effect, spin-dependent effects. So this axion interacts with spin of the particles. So it's a different experiment. We also achieved some improvement here. It's 3 orders of magnitude, but still it's a good example because linear effects may be easier to detect. So now I try to explain, at least explain why it is variant fundamental constant. Okay, no, this I consider only example when you understand what is it about. So, for example, consider this type of interaction. So it's scalar field. I wrote squared because it's physics is more rich, and also maybe first power here. Scalar field interacts with fermions. Masses just give you correct dimension here. So I can introduce this mass into interaction constant. So it's scalar field and scalar made from fermion fields. It's a relativistic Lagrangian, relativistic interaction. But in relativistic physics, there is also mass term, mass of a fermion. And mass looks the same way. It's mass times scalar built from fermions. It's psi bob psi. This is a wave function of these scalars, yes. Or of these fermions, sorry, this is fermions, yes. So this is mass term, how mass appears in Lagrangian, and this is interaction term, how interaction appears in Lagrangian, the scalar field. You see they are alike, they both interact with this psi bar psi or f bar phi. So this is scalar made of fermion field. They look similar. So instead of considering this interaction, we can simply tell that mass is changing. We can combine this term and say, okay, mass is changing. We have additional contribution to mass, which depends on the scalar field. And because scalar field evolves, mass evolves. So we have some evolution of mass. If you have linear effect, it's only cosine because our field is oscillating. So only oscillating effect. But if phi squared here, cosine squared has constant part. Cosine squared is 1/2 and 1/2 of cosine of double frequency. So physics is more rich here. There is non-oscillating term and oscillating term. Non-oscillating term also evolves because universe expands and amplitude of the field decreases because the universe expands. So we have slow drift of fundamental constant. In this case, slow drift of mass, because mass depends on this field. We also have oscillating effects. This slow drift, it's better to look for in astrophysics. Of course, in laboratory too, but astrophysics is natural application because this is drift on a cosmological scale. So we have big band nucleosynthesis, which is sensitive to this, cosmic microwave background, which is sensitive to this, and so on. But if you have oscillating term, the natural place to look is laboratory, because this oscillation may be too fast for astrophysical observation. But for laboratory, like clocks, it's a perfect possibility. So this way we see that searching for variation of fundamental constant may be also interpreted as search for dark matter. Okay, so the same way, so variation of this interaction of scalar field with fermions give you variation of mass term. Interaction of scalar field with electromagnetic field give you variant alpha. It's maybe rewritten as variant alpha. So you add this term to usual electromagnetic interaction, and you see that it may be interpreted as variation of fine structure constant. Fine structure constant depends on the field. And for W and Z boson, it's also variation of mass. Okay, so we have this rich picture how fundamental constant may be interpreted, how interaction with dark matter may be interpreted as variation of fundamental constant. And we also know how to look for variation of fundamental constant. We use all technique which were used for years before, and now majority of the group searching for variation of fundamental constant actually searching for dark matter. I start from the earliest time, which is big band nucleosynthesis, where we have reliable data. And first of all, we try to extract a limit on interaction with dark matter from big band nucleosynthesis. Of course, we would be happy to find non-zero effect, but so far only limits. So of course, if fundamental constant changes, helium abundance, which is sensitive to neutron to proton ratio, number of neutrons to number of protons, and the helium abundance was measured, so we can make a conclusion about a variation of fundamental constant and interaction with dark matter at early time. When there is cosmic microwave background, it also depends on fundamental constant. So you can study variation of fundamental constant and try to find interaction of dark matter at this early time. Then laboratory. In laboratory, we measure ratio of two frequencies. You need minimum of 2 clocks. Just I told you, we measure dimensionless effect. We measure ratio of frequency of 2 clocks, which have different dependence on fundamental constant. They must have different sensitivity coefficients to variation of fundamental constant. So measure ratio with time, we can see slow drift and we can see variation, oscillating variation of this ratio. So it will be linear in mass frequency of variation if it's pi in the first power, or quadratic if pi in the second power. So precision of atomic clocks, as I told, approaching 10 to minus 18, and we calculated sensitivity. And so it's people, a number of groups, including this, as I told, group in Germany in PTB, are searching for dark matter using measurements of variation of fundamental constant. And our new proposal is to use Mös-Bauer transition also, which absolute measurements are very hard here, but fractional measurements, does the frequency change or not, are possible. So these are results, because measurements continues for several years already. These are results for linear dependence, so variation of alpha, interaction of phi with F mu. And this is a quadratic effect, quadratic for phi squared, and effect is phi squared here. Also interaction with F mu. I like this plot because when the effect is quadratic, you can extract results from different places. You can extract results from Big Bang nucleosynthesis, from cosmic microwave background. So it's cosmic measurements, astrophysical measurements. You also can extract results from Dysprosium clock and rubidium cesium clock with hyperfine clock. Cesium is frequency standard. It defines unit of time, second. So, and you see here, it's a logarithmic scale. Improvement in comparison with other measurements, more than 15 orders of magnitude. And this small area of masses, it's more than 15 orders of magnitude, a little bit less than other places. But we have a very big advantage of these linear effects. Improvement is huge. So up to 15 orders of magnitude and more. This is for interaction of field phi with electromagnetic field. So it's effectively its variation of fine structure constant. When we do the same work for interaction of field phi, of stellar field, dark matter, with quarks, indeed huge advantage here. It's Big Bang nucleosynthesis and rubidium cesium. Optical clocks are not good because we are not sensitive to strong interaction parameters. So Big Bang nucleosynthesis and rubidium cesium hyperfine clocks. Hyperfine means it involves nuclear magnetic moment, so it's sensitive to this quark mark over lambda QCD parameter and interaction with quarks. When there is interaction with electrons, again, it's here we have cosmic data only, CMB and BBN, cosmic microwave background, Big Bang nucleosynthesis. Again, very big improvement. Interaction with W and Z boson. We don't have any other data how dark matter interacts with W and Z boson. So it's, you know what is W and Z. It's bosons which are responsible for weak interaction. They appear only virtually in our world. So, and Big Bang nucleosynthesis data give us information about interaction of dark matter with these bosons. When there is Higgs boson is responsible for mass. So we also can study interaction of dark matter with Higgs boson from Dysprosium clock and rubidium and cesium clock. Again, significant improvement. Not 15 orders of magnitude, but 2-3 orders of magnitude improvement compared to fifth force searches, and mostly for small mass of a field phi. So when I briefly mention another possibility, before I discuss some homogeneous distribution of dark matter, but it may be another scenario with dark matter is inhomogeneous distributed. There are some clumps of dark matter, topological defects made of dark matter, both stars and so on, some popular topics. And instead of oscillating effect, here we have transient effect. So when this clump of dark matter, some topological defect, both star passes off, you have sudden change of fundamental constant, maybe for a short period of time. And there are different methods suggested to search for this phenomenon. It's a magnetometers, pulsar timing, atomic clocks, or laser interferometers, like huge interferometers like LIGO and Virgo, for example, which are used to detect gravitational wave. Well, for example, this LIGO, Virgo, GEO600 measurements, how it may be. Of course, they are built to detect gravitational wave. If topological defects or some clump of dark matter passes by, it also perturbs the system. It changes phase of lasers, and it may be detected using these interferometers. The only difference, of course, you need to see that it is not a noise. You need simultaneous detection on several devices, near simultaneous. But for gravitational wave, the speed is speed of light, so it's very small interval between the different devices. But dark matter moves much slower, some like 10 to minus 3 of the speed of light. So interval between the events and different interferometers will be much bigger. So people did not look for it. It's a different time scale. They would reject such event. So to look for coherent detection of these dark matter clumps, they need to consider correlation on a much bigger time scale. No, people are interested. We discussed with experts. They were interested, but no measurement so far has been done in this area. We also can use small interferometers. Of course, small interferometers do not explore so big phases like in LIGO and Virgo, but it may have, say, up to 1 million of reflections. So effectively, we may involve the same effective length as in huge interferometers. Up to millions of reflections, 1 meter is transformed to 100 kilometers. So it's a pretty big time scale, space scale. And if you estimate phase produced on these devices, and phase is wave vector, which is omega over c times length. Omega is frequency is given by atomic unit of frequency for optical transition. Length is proportional to Bohr radius. And if you multiply these two parameters, you see that you get fine structure constant, E squared over hc. So phase is proportional to fine structure constant. So a relative change of phase, delta phi over phi, is delta alpha over alpha. But phase is very big, even in a small interferometer, because length is in meters, wavelength is nanometers. So for a single passage, change of phase is 10 to the 7 delta alpha over alpha, because phase is very big. Delta phi over phi is delta alpha over alpha, but delta phi is proportional to phase. So you have delta 10 to the 7 delta alpha over alpha. But if you have 10 to the 5 reflections, the change of phase is 10 to the 12 delta alpha over alpha. So it's a huge enhancement, really huge enhancement of a phase change due to variation of alpha. And this is a way which is already explored in measurements. I don't want to discuss details, but people are doing measurements using this idea of interferometers. Then pulsars, which are a little bit closer to astrophysics. Pulsars also wonderful clocks produced by nature. Stability up to 10 to the minus 15. It's long-term stability. So we can try to explore it. Especially good is to explore a network of pulsars, similar to possible detection of gravitational waves. Some coherent detection of a, say, passing of clumps of dark matter. So if it passes slowly, we have some change of frequency of a pulsar, some change of the parameters of pulsar. But it's not so exciting. It may cause a pulsar glitch, so sudden change of frequency. Especially good to search for correlated glitches in binary pulsars. So simultaneously, two pulsars have some glitch approximately the same time. The glitch we observed, but nobody ever proved that it's related to dark matter. Of course, we may produce some ideas why glitch in the pulsar frequency may be caused by dark matter. Because pulsar may be treated as two-component system. Neutron superfluid core surrounded by neutron crust. And in superfluid neutron liquid, there may be vortices. Vortices are responsible for rotation of superfluid liquid. And these vortices are pinned to neutron crust. Energy, so vortex itself is macroscopic, it's some 10 kilometers length from one side to another line. But deactivation energy is actually pretty small, it's about 1 MeV. So dark matter, which very weakly interacts with normal matter, may penetrate inside neutron star and decouple, unpin this vortex and cause avalanche of vortices. So angular momentum of vortices is transferred to crust, and this may be a pulsar glitch. Okay, nobody ever proved that it's ever happened, so it's a future maybe try to find dark matter using these pulsar glitches. Of course, it should be correlated glitches in different pulsars, and otherwise it's hard to prove it's due to dark matter. Okay, and finally, maybe nearly last slide, we can help nature, in this case, or help experimentalists and produce dark matter field ourselves, or just scalar field. Because if dark matter interacts with matter, matter is a source of scalar field. So it produces Yukawa field, e to the minus mass over r divided by r. So if field phi is produced, it causes variation of alpha, as we discussed a few slides before. So we can use massive object just to try to change alpha. For example, experiment was done with 300 kilogram piece of lead. It was oscillating piece of lead of big mass, close to Dysprosium clock, and people, again, Butker group, they try to find variation of Dysprosium transition frequency due to approaching big mass of lead. So it's kind of laboratory experiments, but we also have natural sources of scalar field, which may be sun, which is pretty far away, but orbit is elliptic, so scalar field will be slightly different when it moves around the sun. Move also orbit elliptic, so moon field also may change due to elliptic orbit. So of course the measurements has been done, and sun is sensitive to the effect of sun is sensitive to extremely small mass of particles, because we need big range of Yukawa field. Moon smaller range, and smallest range, of course, for lead mass. Its mass of a scalar particle may be some 10 to minus 4 or a little bit bigger. So experiment was done. So it's a search for scalar field, which is Yukawa field produced by massive bodies. Okay, so I finished. Just quickly repeat my conclusion. There is a hint for special variation of fine structure constant in quasar absorption spectra. It may explain fine-tuning of fundamental constant needed for life. So it would be nice to explain this puzzle, which exists for many years, why fundamental constants are fitted for existence for life. It's just maybe because fundamental constants different in different parts of a big universe, and we just appeared in the area where they are good for us. Then new classes of dark matter effects which are linear in the underlying interaction constant. It traditionally thought effects of dark matter scale as a second or fourth power, so second or fourth power of interaction constant. And here, effects of variation of fundamental constant are, it's a linear drift and oscillating variation of fundamental constant, are first power in interaction constant. So we have a big advantage here. And indeed, we obtain up to 15 orders of magnitude improvement on interaction of scalar dark matter with photon, electron, quarks, Higgs, W and Z bosons. So it was useful to get some information about candidate for dark matter, about its interaction. Now, of course, there are a lot of laboratory experiments which are planned. It's a nuclear clock, maybe uranium clocks. It's a bigger transition frequency, but still it may be reached by recent laser-induced coherent field up to 100 eV. When mass bar transition may be a good source. Highly charged ions, which are studied in Heidelberg. So altogether, we have enormous potential for atomic experiment to search for variation of alpha and dark matter with very good sensitivity. And of course, astrophysics is still open field, and people continue to search for variation of fundamental constant in astrophysics, because first hint for variation was obtained in astrophysical data. Thank you. That's all what I wanted to tell today.
Thank you very much, Victor. This was fascinating, and it's a real eye-opener, especially, at least for me, the wide range of parameter space that might be opened up by astronomy and laboratory experiments. So we're running a little late, but so I think there is time for a few questions. If you would like to put your hand up using the reactions button, I will try and see who wants to ask a question. I don't see anything right now, actually. So let me ask a question. I mean, I sort of did a little calculation in my head when you were talking about the astronomical spectroscopy, and I think that you are getting down to about 10 to the -7 in delta lambda over lambda from the point of view of astronomical observations about the spectral resolution. And of course, I mean, I'm not an observationalist, but this gets slightly difficult. But I do know that with the ELT, that number should go down maybe a couple of orders of magnitude more. And it struck me that you have a very sensitive way. I mean, if indeed the change in fine structure constant is related to space-time, and if that is related to dark energy, of actually not just measuring the global equation of state of dark energy, but looking for these asymmetries and variations from place to place in the universe. How do you see the future of this field? Because you know, you've done these measurements, and it looks like it's not easy, but it seems to be feasible in the next decades to get down another magnitude or even two, and it's remarkable.
So I would be happy to see it with improvement by orders of magnitude. So far, it increases mostly statistical. More and more data points are involved. So from 300 to 1,000, but it's still statistical improvement of accuracy. Yeah, of course, it would be good to have a real improvement, which is not pure statistics, high accuracy of measurements.
Yeah, systematics.
Yeah, systematics is a key point here, of course. I understand this because, again, I am not doing measurements myself. My contribution was suggestion of a method and calculations, yes.
Yeah.
So I have to trust my colleagues astronomers.
Yeah, but it's remarkable how big your predictions are.
Yes, and this topic is not simple. I may even call it controversial. So John Webb is big enthusiast, and he believes that he has done everything perfect. So it's perfect measurements and so on. But I'm not sure that other astronomers agree with this, and it must be confirmed. It must be confirmed by astronomical observation, and it's nice to have independent methods like atomic clocks or anything else, which give you the same answer, consistent answer. It will not be the same, but consistent answer.
I see Ralph Klesson has got his hand up.
Yeah, thanks. So thanks for this highly interesting talk. My question may be very naive as a theoretical astrophysicist. So as I understand, on the astrophysics side, your measurements rely on the relativistic corrections and that these are done, let's call it, correctly. And so I'm wondering whether we are sure that these corrections are fully understood, right? In order to calculate the line shifts either in the positive or the negative sense. Is there leeway to simply resort to uncertainties in these calculations for the derivation of the changes of the fine structure constants that you refer to?
Okay, let me clarify a little bit. We do not calculate variation of fine structure constant. We calculate effects of variation. If alpha changes, how big will be change of atomic transition frequencies? Yes, and we don't need high accuracy to do this. 10% accuracy is sufficient. Yes, we don't calculate frequency itself. We calculate change of frequency. You remember this formula, omega 0 plus q alpha square, no, q delta alpha, yes. We calculate only q, we calculate coefficient before delta alpha. And we did numerous tests. In simple atoms with one electron above closed shells, we have results which predict absolute values of frequency to 0.1%. Also, we have unbiased prediction. We did calculations before the measurements. So we predicted frequency of one transition in unstable elements, some super heavy elements. We predict parity violation in atoms before it was measured. it was confirmed to 1%. So we know what our computer codes are good. No, methods also, all of the summation and dominating diagrams were good. And we are sure we did calculations correctly. But with this atomic theory, we do not predict delta alpha. This is a different story. We only calculate sensitivity of transition to variation of alpha. And we did numerous tests. Okay, so voluntary and involuntary. We have some, taken to my age into account, we have 40 years of experience working in this field, actually more. And we predicted a lot of things which were confirmed by experiments. So I don't have any doubts about quality of our calculations, but I cannot comment about quality of astronomical work. I assume it is good, but it's my assumption.
Okay,
thanks.
it's getting very late, actually. It's in Victor's, by Victor, it's 1:15 in the morning. So, so I think we'll just have one more question from Andreas Trautner.
Hey, thanks for the nice talk. So, so as far as I understood you, the variation you see from astronomy in delta alpha over alpha is more or less like a dipole, right? So
gradient of alpha, yes, in space, yes. You can call it dipole. Yes. It's a smooth gradient. It's not like
okay, but you can point it to a direction, right?
Yeah.
Yeah. So how does this line up with other dipoles that or other directions that we observe, like the CMB dipole or the dipole in matter that people claim?
I can show you this picture, so you're probably more experienced than me in this area. I can show you pictures so you can immediately see the direction. Yes, this is CMB dipole. CMB dipole is on this plot. This is a point where CMB dipole directed. This is galaxy, you see Gray's galaxy, yes. And this is a direction of a gradient, or again, astronomers call it dipole, but it's not actually dipole, it's just direction, because it's gradient of alpha. You go further away and effect is bigger, like here, yes.
Okay, well, thank you very much.
Going further away, effect is bigger. So it's not just a direction, it's not constant value. The deviation from present value increases with distance or time. It does not coincide with motion of Earth. Otherwise, it would be trivial, yes. Trivial systematics. It's a different direction.
Okay, thanks.
Okay, well, thank you very much, Victor. Before we thank Victor, I'd like to make a couple of announcements. First of all, if there are further questions for Victor arising out of this fascinating colloquium, could those interested in talking further to Victor please contact Jose Crespo? The email address is in the abstract left on the web advertisement, and he will arrange a meeting when it's convenient. And lastly, before we, I'd like to announce, if I could have the screen, I'd like to announce next week's talk. So next week's talk will be by Ryusuke Hirai, also from Australia, who's going to tell us about what stellar evolution and close binary systems, how they react to supernova explosions and leave imprints of which are observable today in supernova remnants and other types of object. If you have questions for Ryusuke, you can get in touch with Fabian Schneider in advance, who is Rio's host. So now I'd like to ask everybody if they could unmute, and then we can thank Victor for this very interesting talk.